APAB. We are doing 2.3. This is probably our last video in the section. So we are doing particle motion again, which we talked about a little bit before, now with acceleration. Super exciting. Woohoo! All right, so first and foremost, I want to kind of logic through what these different quantities are and what units you would see, if any. Not every problem has units, but if there are units, why you'd see them. And yeah, so anyway. So we've already talked a little bit about position, right? So position is your physical location, right? So if you're on the x-axis, we usually use x of t. So if we were talking about you moving left and right, you'd often see position as x of t, right? If you're talking about movement up and down, like climbing up and down a ladder or moving up and down a wall or moving up and down the y-axis, you'll often see your position written as y of t for position on the y-axis or h of t for height. Also, inexplicably, a lot of books and a lot of tests and a lot of teachers use s of t for position. I've got no good reason why. You'll very rarely, if ever, see p of t, which might intuitively make some sense, but you don't. I mean, position does have an s, I'll give you that. So you'll see one of those. Now, in the examples, I've been mostly using x of t just to show you, but obviously if your position was y of t, then when you get down here, your velocity would be y prime of t, not x prime, right? If your position was h of t, we'd be talking to h prime of t, etc. Okay, so position is, if there are units in position, it's generally a unit of length, right? So 3 meters, 10 feet, 5 inches, right? 20 yards, right? It's usually, and it generally refers to your position from some starting location. If we're talking about the x and y axis, the starting location is generally the origin. But if it's a word problem, the starting location could be the ground, and you could be climbing a ladder, right? So a position of 0 would mean that you were on the ground. If you were talking about like diving, like deep sea diving, your position of 0 might be the water, and then how deep you go in the water might be your position, right? And in that case, it would be negative because you're below sea level, right? So it is worth noting that position is a vector, right? Position has a sign. So if the origin is my starting position and I walk over and stand at the x-coordinate of 2, that's a positive 2 because I'm to the right of the origin. If I walked the other direction instead to negative 5, my position is a negative 5 because I am to the left of the origin, right? So it is worth noting that a positive position is usually right or up, depending on whether you're talking about left and right or up and down, right? And a negative position is usually down or left. And I'm sure there are times that that's not the case, but that's usually what we're looking at, right? So position is a vector. It has a direction. Positive position is usually up or right, which is what we'd expect because that's where we find positive x's and positive y's. And negative position would be down or left, which is where we find the negative x's and negative y's. But I said that backwards, negative y's and negative x's respectively. Anyway. Not every problem has units. You're going to see lots of position, velocity, acceleration problems that don't have units. But if they have units, then you need to pay attention to them. You should not invent units. If there are no units in a problem, there are no units, and that is fine. It's just what it is, right? Okay, so then let's talk about velocity. So in old school, like elementary school thinking, velocity really is just your change in position, which here I used x again, but I could have used any of these letters. I'm just using a sample. Your change in position over change in time, right? If you traveled 200 miles and you did it in 4 hours, your average velocity was 200 divided by 4, which is 50 miles per hour, right? So it's the rate of change in position. When you think about it as a change in x over change in time, the units make a lot of sense. The units of velocity, if there are any, are some kind of length over some kind of time, because it's change in position, which was measured in length, over change in time. So it's not a surprise that this is the derivative, because remember, this delta symbol can also be written as a d for a little teeny change. So dx dt would be the derivative of x with respect to t, or x prime of t, right? So velocity is usually, it's safe to abbreviate velocity as v of t, but it is worth noting that v of t is the derivative of position. So v of t is equal to x prime of t, or y prime of t, or h prime, or s prime, whichever of those functions you're using. So again, to get from position to velocity, you differentiate, right? Remember, if you think about a derivative as a slope or a rate of change, it's going to make your life a lot easier. The rate of change of position is called velocity. Most of us feel comfortable knowing that, but as soon as you start throwing in derivatives, and right now it's not super stressful because you only know how to go one direction right now. You know how to differentiate. You don't know how to integrate yet, which would be going the opposite direction from acceleration up to position. So since you only know how to go one direction, you can't as easily go do the wrong thing because you don't know even the other option, right? So again, position, differentiate, you get velocity, right? We've seen that before. Now what we hadn't talked about before, because we didn't know how to take a second derivative, is acceleration. So acceleration is the rate of change of your velocity. Remember, rate of change and slope basically mean derivative. So rate of change of velocity means differentiate the velocity. So my a of t, which is what we usually use for acceleration, is the same as the second derivative of position, meaning x double prime of t or y double prime of t, and it's the first derivative of velocity. So again, to get from position to velocity, you differentiate. To get from velocity to acceleration, you differentiate. Because this is the rate of change of velocity over time, it's going to be the unit of velocity over the time unit. So that's length per time, which you will often see as length per time squared. But again, the reason it's that is because length per time. Now, one way to think about this logically, and an example would be like meters per second squared, right? One way to think about this logically is every time you differentiate, you're dividing by time again, basically. So when you had meters, if you differentiate once, you now have meters per second or meters per whatever the time is. If you differentiate again, you have meters per second squared, right? An interesting side note that's not going to come up on your calc test, but it's just fun because one of the fun things about, well, one of the good and bad things about math is that it's a bit elitist, right? And so the notations can be difficult, sometimes inaccessible, and if you don't know how to read something, you can feel really dumb even if you're not dumb because you just don't know what something means even though you have the ability to comprehend high-level mathematics. So a fun sort of inside math joke is that the third derivative of position, so x prime or x triple prime of t, or you'll often see it as d cubed x dt cubed, right, is called jerk. This makes sense if you, and this is not like me making up a thing, this is actually a thing, right? It's called jerk because actually if you think about what your body does when your acceleration changes, right, we already saw that acceleration was the rate of change of velocity. So differentiating again to get jerk would be the rate of change of the acceleration. Well, if your acceleration changes rapidly, your body physically jerks, right? If you have your foot on the gas pedal, right, and you're moving forward and you're accelerating positively, moving forward, but then you slam your foot on the brake because you see a ball roll across the street, or you see a squirrel or something, right? You slam your foot on the brake. When you slam your foot on the brake, your body physically jerks in that car. Jerk is an actual physical quantity, and it is the rate of change of acceleration. It is the third derivative of position. So it's also a really good math insult. I'm just saying, if you wanted to call somebody something, you can be like, oh my gosh, you're such a third derivative of position, which is fun and super hilarious. You don't have to, but you know. Okay, so let's now that we know a little bit about acceleration, I'm going to add a little bit more to your particle motion vocab, okay? So we already talked about things like at rest, right, meaning velocity is 0. So here's the vocab we already had, and hopefully you already have note cards for this, right? So we know that the word initially should go with, so I'm just going to put a little arrow, should go with t equals 0, right? We discussed that when you read the word at rest, or the phrase at rest, it should tell you that velocity is equal to 0. We discussed that moving either right or up should tell you that velocity is positive, right? And that moving left or down should communicate with you that velocity is negative. Oh, as a side note, when I said you should make note cards for this, and some of you were probably like, oh my gosh, you're kidding me. On an AP, on a free response, you are probably getting a point just for communicating the understanding that you read this and you knew it meant this, and you knew to set the velocity function less than 0. I kid you not, knowing these phrases and knowing instantly what they translate to is incredibly important. So please, please, please make a note card, right? One side, other side. Okay. So those are the ones we've done so far, right? So let's add a few more, okay? So if you hear the phrase speeding up, okay, and for the record, that's actually the same thing as the phrase speed increasing. Okay, what that's going to mean is that A and V, so acceleration and velocity, have the same sign. And I'm going to walk you through that in just a sec and explain to you some logic of why. And if you hear the colloquial phrase slowing down, right, slowing down is actually the same thing as saying your speed is decreasing. Then that's going to mean that A and V, acceleration and velocity, have opposite signs. Hopefully I'll remember this at the end of this after I talk about these, but I do want to address what speed is because we haven't actually expressly talked about that yet. So let me walk you through the 4 possible examples that you have with acceleration and velocity to show you why I'm speeding up. Okay, so let's pick the obvious ones first, okay? So I'm in a car. This is my car. It doesn't look much like a car, but you're going to survive. Okay, so I'm in a car. I'm driving forward, right? So I'm driving forward, which means my velocity is positive, right? I see a yellow light, which would be the middle of the 3 lights, right? So I see a yellow. Okay, and I am a good driver, right? So scenario 1, I am a good driver. Okay, I see a yellow light and I hit the brake. What that means is that my acceleration is now going to be negative, right? Because the brake is the opposite of accelerating, right? So sure enough, I am slowing down, right? And that makes sense intuitively. If you picture yourself being in a car, right? If you picture yourself being in a car and you're driving forward, because that's the only way to drive, right? I mean, I know you could do on reverse, but just assume you're driving forward. You see a yellow light, you hit the brake, which makes your acceleration negative. Boom, you're slowing down. See how A and V have opposite signs, right? Let's say that I am a bad driver. Same situation. Okay, there's my car. Again, not very car-like. It's cool. All right, my velocity is positive. I see that yellow light. Right, I see my yellow light. And I speed up. Like, so I put my foot on the gas. Right? And it's funny because even just walking through this, I said the phrase that I said speeding up, right? I said, so sure enough, if you see a yellow light and you're already moving forward and you put your foot on the gas, your acceleration is definitely positive and you are totally speeding up trying to make it through that light, right? Okay, both of those feel hopefully pretty intuitive. The ones that tend to feel less intuitive are what happen when our velocity is negative, because to be perfectly honest, most of us don't really think about negative velocity very often. We think about the motion that we're traveling as being positive. So I'm going to give you an example where I am in a helicopter. This is my terrible version of a helicopter. Okay, I jump out of the helicopter. My velocity is definitely negative, right? Because of gravity, my acceleration is also negative. In fact, it's a negative 9.804 meters per second squared. So my velocity is negative, my acceleration is negative, and I am absolutely like here's me, right? And I am plummeting to my death, going, ah, right? I am definitely speeding up. Now, there's always somebody who's going to be like, but what about terminal velocity? Okay, you're right. At some point, I stop speeding up. You're a physics champ. It's cool. But the logic being, I jump out of the plane or the helicopter or whatever, my velocity is negative, my acceleration is also negative because gravity, and I am definitely speeding up. I understand that there is a terminal velocity, but let's just ignore that for a sec because that's not the point. And also, terminal velocity is because you have things like air resistance and other things. Like we're in free fall, we are assuming that this is in a free fall in a zero in a vacuum is what I should say. Like so I'm speeding up. Okay, cool. All right, so now let's do the other scenario. I'm in the helicopter. Okay, again, my terrible version of a helicopter, it's fine. Okay, I jump out of the helicopter, but after I jump out, I open my parachute. Okay, now my velocity is still negative, because when you open your chute, you don't stop going downward. Your chute isn't like a magic flying machine. Now my body will jerk upwards, and that makes a ton of sense because gravity was pulling me down with a negative acceleration, right? And then when the chute opens, the air resistance created by the chute essentially jerks my body because my acceleration suddenly becomes positive. So because of the air resistance, my acceleration is now positive, right? I'm not actually moving up. My velocity is still negative. The chute doesn't move you up, but it does jerk your body because your acceleration changes so fast. And sure enough, I'm slowing down. So the reason I bring this up is because at some point, the AP is probably going to ask you one of these two questions. And the answer to these questions is really just knowing about the signs of acceleration and velocity. So, which is once you know that, if you can communicate that that's the information you know, and if you know that's what you need, it's going to be a lot easier to do the problem. So those are the 4 options when you talk about speeding up and slowing down. I do want to address speed real quickly versus velocity, because we actually haven't done that yet, and I did just talk about speed without mentioning it first. So remember that v of t, which is velocity, is a vector. So if you haven't had physics, because some of you haven't, that means that it has both a size, right, a magnitude, and a direction. Okay, so my velocity can be negative. I can be falling out of that helicopter, right? I can have negative velocity. But speed, so the absolute value of velocity is called speed. And it's a scalar, right? I should say a vector because it's a noun. Okay, so it's a scalar, right? So it's a scalar, which means that it's got magnitude only. So when you think about driving in a car, you probably think about speed more than you think about velocity. So if a police officer pulls me over for speeding, right, he's gonna say, oh, Miss Hogan, you were going 75 miles per hour. He's not gonna say you were going negative 75 miles per hour because you were driving south on 95. It's not what's going to happen. They're not pulling me over for my velocity. They're pulling over for speed. So speed is just the numerical quantity. It doesn't tell you anything about the direction. So if I'm plummeting out of that helicopter, my velocity is negative, but my speed is positive. My speed is just how big the number is of how fast I'm falling, okay? So that's just kind of the idea. So let's, now that we know a little bit of vocab, let's do a little bit of stuff and things. Ooh. I just had a thought. So some of you have already had physics, and some of you haven't already had physics, but in Algebra 2, and often in a physics class, you are sometimes given a formula that looks like this in physics. So in physics. Now remember, earlier in this class, not this particular video, but sometime in another video, I mentioned to you that there are two different kinds of physics. There's algebra-based physics and calculus-based physics, because if you don't know calculus, there's a whole bunch of stuff that you just can't figure out and you have to be handed. One of those things that you frequently have to be handed is this formula. So the height of an object in free fall is generally given as 1/2 gt squared plus v naught t plus h naught, right? So where we are told that g is the acceleration due to gravity, v naught is the starting velocity, right? So starting velocity meaning when t equals 0, right, or initial velocity, and h naught is the starting or initial height, right? So starting or initial height, which is saying when t equals 0, okay? So the thing is that if you don't know any, and h of t is essentially the height of the object, right? So it's a position. So h of t is height, which is a position. If you don't know any calculus, you kind of just have to memorize this. And I'm going to be 100% honest and say that I do not have this memorized, not even a little, not even one smidge of this is memorized in my brain, because I know calc, so I don't have to. So interestingly enough, and this is not an example, this is just walking you through one of the many ways that if you know calc, physics is a whole heck of a lot easier. If I wanted to find the velocity of this thing, right, the velocity of this thing would be the same as h prime of t, right? So this whole thing's a coefficient, right? So if I differentiate, the 2 drops down in front, and I would just get a g times t plus v naught, and then since h is a constant, it's gone. Well, what I want you to notice is, I want you to note that if I plug in v of 0, I get 0 plus v naught, meaning I get v naught, which totally confirms that v naught is the initial velocity, right? If I wanted to find the acceleration, it would be h double prime of t, which is the same as v prime of t, which would mean differentiate this, and I'm just going to get g. Remember that g was the acceleration due to gravity. So, when you see this, when you see this formula, right? A lot of times in physics with algebra, you have to just gut out memorizing some stuff that if you know a little bit of calc, you don't really have to memorize all that much stuff at all, which is kind of helpful and super nice. Okay, so let's walk through an example. I think the last ones that we did were 8. That can't be right. No, we did 7, 8, and 9. I don't know, man. It's the worst. Okay, I'm the worst. All right, cool. So I'm going to put an example with a question mark because it might not be the number I think it is. I think we're probably on 10. I'm going to put example 10 with a question mark. If it's actually 9, I'm sorry in advance. Okay, cool. So let's, let's say that the position of some particle on the x-axis, so Bailey is my dog. He's sleeping right behind me right now. He's not actually running anywhere. So Bailey is running on the x-axis. So his position is going to be x of t. For t greater than or equal to 0, such that his position is given by x of t. I could have done like b of t for Bailey, but it's cool. I'm just going to do x of t. Let's do t cubed over 3 minus yeah, okay, that's fine. Minus 3t squared plus 5t plus 2. Okay. Cool. So there's Bailey's position. Okay, just randomly made up. Okay, so we're going to walk through, and we might not do a E10 of this. We might just walk through it. We'll see. Okay, so A, write an expression for V of t. B, write an expression for A of t. C, what times is Bailey at rest? I'll put times in parentheses because that means there could be one answer or there could be many. And cool. We'll start there. We have other things to do with this eventually, but we'll start there. Okay, so I have this x of t, right? That's his position. He's running along the x-axis. He's not actually. He's sleeping behind me. He's a sweetheart. Okay, so v of t is x prime of t, right? So in order to find v of t, I need to differentiate. So if you want to rewrite this, like if you need to rewrite this as a 1/3 t cubed to make it easier for your brain, that's totally fine. If you don't, that's also fine. When I differentiate by dropping that 3 down in front, the 3 and the 1/3 are going to cancel. So I'm going to get that my v of t is going to equal a t squared, right, because the 3's cancel and I drop the power 1, minus a 6t plus a 5. So there's my expression for v of t, right? My next expression for a of t, well, that's going to be v prime of t, or x double prime, right? So I'm going to differentiate this and get 2t minus 6. And then the last question I asked here was, at what times is Bailey at rest? So when you hear at rest, right, your brain needs to think v equals 0, right? That's what your brain needs to jump to right away. That's why you want to make a note card, right? So I set v equal to 0, and because it's a quadratic, I can either use the quadratic formula or I can factor to solve. I'm going to factor into t minus 1, t minus 5. So either t minus 1 is 0, which would be t equals 1, or t minus 5 is 0, which would be t equals 5. So my answer to part C is t is 1 or 5, right? Now, if either of those had come out to be negative, I would exclude the answer because I was told that the problem starts when t equals 0. Sometimes problems have a domain of all times, but in most of these problems, there is some sort of a time restriction. So in this case, it's t is greater than or equal to 0. Right? We're going to do a ton of these particle motion problems later, and you're going to be asked to do a lot of other stuff with them. But this is sort of a decent introduction to some particle motion. We'll definitely do a lot more moving forward, but this is a decent start. So, yeah, we'll end this one here.